going over these two right here, number one. Alright. So we have a function, a cubic function that looks like so. Yes? I'm not? Okay, thank you. Alright, so here's the first f of x. Alright. Alright. Alright, so what are the real important points right here on this function? A and C. That's where the derivative is equal to 0. So if I graph f prime of x, I at least know that the output, the slope of the tangent line, the output of the derivative is 0 right here and here. So at A, the y value is 0. At B, the y value is 0. Well, what happens here? What is my slope? Positive. 2, and it's going to be, what shape is this creating? A parabola. A parabola. Alright. Yes, it is. Sorry. I keep getting that mixed up. B is actually an important point because it's where the derivative slope is 0. So when we graph f double prime of x now, let's go ahead and graph f double prime of x. And so right here. So what, if I look at the second derivative, I can glance at the first derivative and try to look at the slopes of its tangent line. What are the slopes of its tangent line right here? Negative. So the second derivative's output is going to be a negative value. What's its slope at B? 0, and then positive. And we should know that the derivative of any parabolic function is going to end up being some sort of a linear function. Very good. Positive on the right because of the positive slopes, negative on the left because of the negative slopes. There we go. And of course, if we were to graph the third derivative, what would its value be? What's its? It would be a positive value. It would be a constant. Yes, it'd be a constant. We don't have to do that though. We'll box that up. Think about it later. Okay. All right. So, what does a couple questions? Here, the second derivative is negative. It's a negative value. What does that mean for the original function between, there's A, there's B, there's C. Between negative infinity and B, what does that mean for the original function? Say what? Concave down. Concave down. And the double derivative being positive makes us aware that the original function is concave up. Very good. All right, moving on to the next function, the absolute value function. All right, so right here, what type of, excuse me, let me scroll up here. What type of sharp points, what do we call them? That was like 2 units ago. A cusp. Very good. Cusp. Now, that doesn't mean much now, but you'll understand here in a second why it's important or why it's relevant at all. But I'm just going to go ahead and give you the graph of the first derivative right here. Because it was very difficult, and I want to know how many people actually got this, because it was difficult. Did anybody get something like that? No. No? So we got to be able to see in two parts right here. Okay, what slopes do we have right here? Negative constant slopes. To the left of A, we have negative constant slopes. All right. So our derivative should be a negative constant. Makes sense. Negative constant, negative constant. Well, at A, it does a total like 360, and then it starts going to positive constant slopes. So it should be a positive constant. And then at A is what tangent line exists at A? Multiple tangent lines exist at A. Can you have more than one tangent line?
No. Told you, Daniel.
No. You can't have more. So is the derivative's value actually valid, right? Does it even have a value? It doesn't even have a value. The derivative does not exist. It does not exist at the cusp. Because at the cusp, you're talking about the slopes jumping from one slope to another. All right? So here we go. That is the derivative. And I want y'all to think about what these slopes are right here on the derivative so we can get to the second derivative. What are they all equal to? They're all equal to 0. Sorry, let me move that up a little bit. Yeah, so what's the second derivative going to be?
Ooh, I did get that one. I did have it right first, but no.
And the second derivative, look, A, open circle, Y. Can you have a tangent line and an endpoint? You cannot. And then what value is a slope to the left? What value is a slope? 0. And then what value is the slope to the right? 0. Guys, we're going to keep drilling this. Okay? So let not your heart be faint. We will continue practicing this stuff. Alright, so what I want to do is I want to go over numbers 3 and 4 today with y'all on your homework. I'm going to give you an example of each, and then hopefully you'll have time at the end of class to work on that, and I'll have time to review your homework and get it back to you. If not, I will get it back to you as soon as you walk in the door tomorrow, because y'all need to keep a hold of this and keep it with you. Alright, so here we go. What's that? No. I'm not finished with that. Alright, so here we go. Example 2. Oh, actually, we've already done 2. Okay. So, all right, example 3. What we have is a right circular cylinder.
I didn't even know what that was. I tried last night and I was like, what the heck is that?
Can I get the paper with the problems on it?
Yeah. I don't know where my extras are. I've lost them. Alright, I might have to look them up on my... Microsoft Word. Where's my Microsoft Word?
Right there, over, yeah.
I can't see today. Optimization homework set?
Yep.
Okay. Alright, so we're doing an example for number 3. A container in the shape of a right circular cylinder with no top So let's write down our right circular cylinder on our paper. I'll show you. I'll show you. We're just listing all our important information. And it has no top. It has no top. So let's write that down. No top. And let's change the surface area to 16 pi for example's sake. 16 pi feet squared.
How about if I divide this and then they can see
Sure. Thank you.
that?
Okay. And then we want to maximize the volume, and we want to find the height and radius. Okay, so the first thing we need to understand is we need a good model, and a right circular cylinder, that's just a regular cylinder. It's got a right angle as opposed to a non-right angle. So this is what a non-right angle would look like, Tommy. If I had a cylindrical base and then it was an angle like so, an angle like so with the radius. Alright, so yeah, a non-right circular cylinder would be simply a tilted cylinder. Okay. Alright, so here's our model, and we know our variables, bless you, our variables need to be R and H. R and H. So our model is good to go. Alright. So, bless you. First thing we need to do is write down our primary equation. Our primary equation is what we're maximizing. So we need to know the volume equation. The volume, and the volume equation is simply any prism. This is a prism. Alright? Any prism is the volume is the base times the height. The big base though. Big base. Alright? What is big base talking about? It's talking about the area of the base. So what is the area of this base? No, the area of just this base. The formula. Pi r squared. That equals the big base. Okay? So I'm going to convert that into volume equals pi r squared h. What's the problem with this primary equation? 3 variables. We got 3 variables, so we cannot take a derivative and optimize it. Okay? So we need a secondary equation. The secondary equation, in this case, has to deal with the information given, surface area. So how do we find surface area of a cylinder? Let's take a look. We know it's going to be surface area. So let's break down the surface area into its various parts. Okay? So, starting with the base, we know we have an area of pi r squared on the base. What about the height? I mean, not the height, the top. Do we include the top in our surface area equation? No, because there is no top. Okay, So it's just pi r squared. If it was a top, it'd be 2 pi r squared. There'd be two of them. So here, now we need to find the area of what's around. Now how do I do that? I gotta unroll that. You know, you go to the store and get those biscuit things. You stick a fork in them, and they pop, and you unroll it. So you don't need no fork? Okay, so you don't need a fork. Alright. So what we want to do is we want to roll this out. Alright? So if we roll this out, notice I've got it curved. I didn't roll it out all the way. You got to imagine now you had this cylinder and you just rolled it out, right? So what's the area of this? Well, we know it's the length times the width, or vice versa, however you want to call it. But what is the width really in this context? It's really height. So mark out width. That's height. Now the length, what is that really in this context? Very good. Who said that? Alright. The circumference is correct. Because if you roll that out, then this distance here is really this distance here. What's circumference equal to? 2 pi r. So this is really 2 pi r. Okay. So what's the area of the wraparound? Yep. 2 pi r h. Okay. And it's not like yesterday where there were 4 faces. There's just one face. Just one wraparound. So the surface area is pi r squared plus this 2 pi r h. So we can write the formula now. Alright. Pi squared plus 2 pi r h. Pi r squared. Whoop. Surface area equals pi r squared plus 2 pi r h. Now, I know that I'm going to have to use some information here. Because if you look, I still got 1, 2, 3 variables, so I've got to use some information, a parameter, if you will. Plug in your 16 pi r squared, 16 pi feet squared into your surface area. So let's work this out. No need in putting feet squared into this formula, just 16 pi. Uh-oh. Pencil down. Alright. So, let's look at the purpose. The purpose was to replace H, R, or V. Which one do you think we're going to replace given this secondary equation? H, because it's by itself, it's easy pickings. R would be difficult. So let's solve for H.
Coach Berenson?
Yes, ma'am.
Could I see Alex Little in the office for a moment?
Yes, ma'am. Okay, so we minus the pi r squared. Next step, divide by 2 pi r. Now, it's been my experience that simplifying now is not necessary, maybe, because you're always going to have to simplify later. So why don't we keep it like this instead of busting it up into 2 fractions? If you want to bust it up into 2 fractions, that would be fine. It would end up being 8 over r minus minus r over 2. 8 over r minus r over 2. So we're going to put this h into that h to get rid of the variable h. Alright, so here we go. And we need to simplify this. Obviously, we don't want to take a derivative of that. Okay. So here's the funny part, the funky part. What would this end up giving me when I distribute? All right. Why am I multiplying times the top? By the way, let me back up. I don't know if I'm being clear here. Uh-oh, I think another pencil just bit the dust. Oh, it's got a little life left in it. This is really pi r squared over 1, yeah? And so, just so I don't confuse anybody, this is pi r squared times parentheses 16 pi minus pi r squared over 2 pi r. Now this is very interesting right here. What could I do instead of multiplying right here? What could I do first? Cancel out this r and which r? One of these, right? One of these. So it would be v equals, and could I do the pi's too? Absolutely. This pi and this pi, they would both go away completely. Alright, so now we're just having an r times 16 pi minus pi r squared all over 2. Alright, we cool with that? So let's just distribute now. Now I'm still upset with this. It's not good enough for me. I'm not ready to take a derivative. What can I do? Factor out a what? Pi? You could factor out a pi r, but then that would lead you to the product rule, because r is like x. Can't combine like terms. One has an r, one has an r cubed. I don't wanna have that 2 in here. I could divide both by 2, or I could factor out a 1/2. So what do you want to do? Divide both by 2 or factor out a 1/2? It's up to y'all. Whichever one's easier. Dividing's easier. Yeah. So v equals 16 pi r divided by 2 minus pi r cubed divided by 2. 16 over 2 is 8 pi r minus, this is really pi over 2 r cubed. Now I'm ready to take a derivative. Okay. So I want everybody to go ahead and take the derivative of those. Go ahead and take the derivative of the volume, and then I'll catch up with you. If you had factored out the 1/2, it would have looked like this: 1/2 16 pi r minus pi r cubed, and then you would have just taken the derivative of this, and you would leave that alone. Why would I leave that alone? Why would I leave that alone? Multiplying constant. I can leave it alone. But let's just take the derivative of what we got. Go ahead, go ahead. Oh, I'm almost out of room. Oh no. Almost out of room? Alright, guys. Some of y'all might be scared of this. Let me calm you down a little bit. This is a multiplying constant. R is like X. R is like X. And V is like Y. What's the derivative of Y? Y prime. So V, derivative of V would be V prime equals 8 pi, because that's just a constant. This is really R to the 0 minus 3 times pi over 2 is 3 pi over 2 R to the second. Alrighty. Y'all know what to do. Optimize time. Set it equal to 0 and solve. Alright, find your solutions, and then I'll catch up to you. Minus 8 pi from both sides, then multiply by the reciprocal. That would be the quickest way right there to get r squared by itself. Yes, negative. Alright, so you'd end up with this, Tommy, 3 pi over 2 r squared, and then you'd multiply by negative 2 over 3 pi. What are these what is the negative's purpose? Cancel out the other negative, and the 2's and the 3 pi cancel out, and over here you multiply by the same thing, negative 2 over 3 pi. Okay, this is really 8 pi over 1, so it goes up top, multiplies with the negative 2, makes 16 pi over 3 pi, and that equals r squared. Let me move over here, get some more room. Alright, so what happens with the pi's? Cancel. R squared equals 16 over 3. And then I take the square root. And of course, plus and minus. And what's my more simplified answer?
4 over the square root of 3.
Yeah, 4 over the square root of 3. Plus and minus. Okay? Now, can you have a negative radius? Alright, so, or r equals 4 over the square root of 3. So this is the radius that is going to be the maximum. It's going to maximize your volume. That will be this radius. So we also need to find the height. What do y'all want to do to find the height?
Plug it back in there.
Plug it back in there. Okay, so we have options. We can plug it into many different steps here. Wait a second. Oh, that's all the way up there. Alright, so you can plug it into here. That would work. Actually, plugging it into any of these would work, but this is probably the best one. So in your calculators, you need to do 16 pi minus pi times 4 over square root of 3 squared divided by 2 pi 4 over square root of 3. Alright, let's find out what we get for h. Alright. Any questions? It's all calculator work from here. You're confused on how to plug it in your calculator right here. Maybe I can help. Alright. So we got 4 over the square root of 3. Right? So if we're using this equation right here, that would be 16 pi. Oh, clear. 16 pi minus pi parentheses 4 divided by the square root of 3. Oh, gotta get out of your radical. In parentheses squared equals, that's on top, that's your top value, and then divided by in parentheses now 2 times pi times in parentheses again, because I just feel like fractions have to be in parentheses. That's how I roll. 4 divided by the square root of 3. Oh, get out of my radical. In my parentheses. In my parentheses again. That's what I got. Everybody get the same thing? Okay. This is why you need a graphing calculator. You do not want to do this on a normal calculator. And when you do your optimization test, you will have to, do that. Or, we could just plug it in and manipulate all the fractions and come up with a fractional answer. That's what I would do. Alright. H is 2.309. And we're done.
So we did all that work 28.
Yep.
And R.
Oh, my bad. And R. Well, mainly 8.
Yep. Okay. Alright, so I want y'all to work on, if you're done with number 2, that's awesome. I'll be checking that tomorrow. I'll go ahead and work on number 3, your number 3, and you should get a lot of it done. So you shouldn't have that much homework tonight for your number 3.
So all we have to do is number 3?
Yeah, well, 2 and 3. I don't know which one I'm going to check. You should be most of the way done with number 2. Alright. I hope this recorded. It's better have it recorded. Oh yeah, it is.